Good morning. This topic is about the probabilistic method of power estimation. The reference for this topic would be the Gary chapter 2 and Kaushik Roy chapter 3. In the low power IC design course, we have studied already the simulation approaches for the power analysis. That means the power estimation, how we do through simulations, and these simulations could be right from device level, the circuit using them, and this could be gates, or this could be some logic functions what you have, so functional level. So even bigger than that, some modular level you may have, and beyond that you had the functional blocks, and beyond that you had architectural level. Through all these we were able to have some idea about how the power could be estimated and how the power analysis could be done, and you had various ways to have low power design done for low power IC. This is what we want, low power IC. And in this process, how long do you spend in doing the analysis? That is going to be a very important criteria. In the case of simulation approaches, whether you do in device level or the architectural level, you would be having the characterization of the device or the functional blocks, the modular blocks or the logic functions, gates, and all these. First, they would be characterized. This characterization process is going to be a very meticulous, very carefully done one, because using this characterization only you will identify a small module, whether it is a gate or something I don't define. It could be a device itself, or it could be a gate, or it could be some other modular function what we have. And after characterizing these particular modules, I go for using these in my bigger system design. And since because I have done this characterization well before, and the characterization happened to be very accurate, and I go for spending so much of resources on this, time on this, I go for full custom designing my gate, and then I characterize, and based on the characterization what I find, I go for even tinkering with the design once again, and I go for getting the best gate structure possible. Then I use all such gate structures in my final design. That enables me to go for having the low power design analysis through your simulation based approaches. And through these simulation based approaches, I go for making use of our EDA tools you had been using. For example, the Cadence tool what you are using, and the Xilinx tool what you have, Altera, all these, they have modeled the circuits inside, and the use of such idea is enabling us to go for analyzing the power what we have out of the circuit while operating under such conditions, under maybe it's even the temperature parameter, or the worst case best case models. That is what you have studied already, which help you to go for working with various process corners models for your applications. When you go to really work in the field, your circuit should be able to withstand everything, and all these are made possible through the simulation approaches so nicely. Simply said, your PSpice or your Cadence Spice, Spectre Spice, what we have, they were dealing with, they normally you go for considering the voltage across any component at the two ends of the two terminals of the device, the current through any loop you have, and you go for simulating that over a particular time t. And this idea is helping you to go for identifying how the particular limb, the edge of your circuit is working. The edge is, what I mean is the component what you have between two terminals, between two nodes naturally. And when I have some billions of transistors in one complete circuit, how do I able to go for identifying the I, the V, and with respect to the time also for various input conditions. This is what is actually making the process of simulation based approaches time consuming, and it needs manpower, but it gives you so much of accurate results. So wherever I would want to accurately define my system specifications, I would naturally go for selecting the simulation based approaches. But given a certain application in which I would just want to approximately identify whether the system would work fine, I need not go bothering about my corner models analysis, the Monte Carlo approach, what we can do for various parametrical variations, or even for the big system what I am going to be taking. I need not spend days and days together for simulating for various input conditions to see the corresponding outputs. In such cases, we have the probabilistic method of power analysis to be coming to our help. This is what we will have in this particular session, that is about the probabilistic power analysis. In the case of probabilistic power analysis, we would be making use of the statistical theory to our advantage. When I talk of statistical theory, when I have a signal with me, and this signal I am going to call it as random because I won't know. I have millions of nodes in my circuit, and each of the nodes are having either a logic 1 at it or a logic 0 at it. So all these processes are random 1-0 processes. And I cannot, when I go for considering a big system with so many different nodes in that, each and every node could be a 1 or a 0 when I consider them, naturally I will not be able to, since because I am calling this as a random event itself, I am not going to be relating as it is in the first go when we discuss. I am not going to be relating with the time. No time based events I am going to be considering. But I would be considering each and every node whatever I take, whether they are in 1 condition or whether they are in 0 condition, I can know. Whenever I say it was previously in 1 and it now is going to 0, that is a 1 to 0 transition or a 0 to 1 transition. As you know, I have my pull up network, I have my pull down network. This is our basic theory what we had been studying, and I have this as the CMOS circuit. This is consisting of PMOS devices, and these are your NMOS devices. I have my VDD and I have my ground connected here. I take the output, and whenever I say I am making this a logic 1, that means I am charging this particular thing to the maximum VDD potential whatever I have, and in that process I am spending half CV square, and the moment I let all this go off to the ground, I spend another half CV square, and then I say that I have CV square for every event multiplied by your frequency is going to be giving me the total power dissipation in the particular circuit. And why don't I use this? Because I know in probability theory I am considering these nodes as having 1 or which are becoming a 0, or some nodes at 0 which are going to be becoming a 1, and all these transitions are now going to be literally helping me for getting the power dissipation measurement done. But I don't know particularly. I will give you with a specific example itself later. Right now we will assume that every 1 to 0 or 0 to 1 transition is getting some power, is making some power dissipated in the circuit. So if I have some billions of nodes also in my system, there is no problem for me to identify, to calculate the power. But how accurate they are going to be? Of course, this method is not going to be very good for accuracy. But given with the computation efficiency, this is going to be better than our simulation based method. And particularly for gate level abstraction and characterization, this is going to be the best. How this is going to be helping us for the power analysis, we will see, and we will start first with a random logic signal. By random logic signal, I would mean this sort of a signal. For example, at 0 time it is at logic 1, and at 5 time it is at logic 0. At 15th instant of the time I have logic 1. These are the states of switching what I have for my current logic signal. This is a logic signal and I go for characterizing this. How do I do? At 0th instant it was at 1. It is followed by 0 at the 5th instant of time. It is followed by once again a 1 at 50th instant of time. This way, for as long as the observation time is, I could identify by the sequence of the value and the time at which all these went on. And this way of representing a signal would be naturally very tedious. That is what I mean to say. A 1 and a 0, the logic signals what I have, which are randomly happening, and these signals, if I want to represent, I should identify this way. But the events, when they actually happen, do I need to identify them for representing how many times I have 1 and 0 switchings taking place in this particular signal? I don't need. Now consider another set of signals. This is signal 1 and signal 2. I count the number of switchings what is taking place. At 10 it is 1, and at 30 it is second, 2, 3, 4, 5. And here too I find the same thing as you have seen before. But can I say that these two signals are the same? They are not. They are not actually. If I go for representing them as 5 times they are switching, each of them, doesn't mean that both the signals are the same. If I need to calculate the power dissipation for the first logic signal and the second logic signal, I will naturally end up with the same CB square F formula and the same value I would be getting. There is no way of identifying how actually these were changing states and for what amount of time they were actually in what type of state. All these are not there for us to infer from. Therefore, there has to be a way in which we would go for a deeper insight into the use of probability theory for our gate level power analysis methods. So first we would talk about the continuous, how to represent the continuous and discrete random signals. Whenever I say it is a continuous random signal, the signal transition, whatever I consider, the signal transition can happen at any point of time. I am not going to be delineating them with respect to any particular time instant, at any time. Whereas when I talk of the discrete random signal, as we all know, all the digital circuits are guided by the common clock what is traveling throughout. Whenever a transition is happening in accordance with the clock timing, or at least if I consider this as a clock signal, multiples of clock signals, if I go for taking for the signal transition, then I would say it is going to be a discrete random signal. This is sort of a special case of continuous random signal only, but this is going to be helping me for identifying the signal transition only at the time when I have the clock also transitioning. This would help me in better identification of the probability and the frequency of switching of each and every node. In relation with that, let us define what is the relationship between the probability and the frequency. Probability and frequency. We can very simply say the frequency is going to be, as we have seen in the previous slide, if I have the number of switching, I go for comparing my logical transition over a particular time t I had taken, and during this time t, whatever be the switchings which were happening, I would call this as n of t. And if I am going to be finding out the average, I would very simply say it is divided by t, but I am not going to call it as divided by t, because one frequency, if I say it is one cycle, it has to have a positive transition and a corresponding negative transition also. So I would put this as n of t by 2t when I am considering the transition time, the whatever be the observation time as t, n of t by 2t is going to be my frequency. Therefore, when we specify f is equal to n of t by 2t, where n of t is the number of logical transitions what we had over time t, and in continuous signal model we are not actually specifying the time, therefore the time is considered to be infinity. In such a case, with the observation period of infinity, we would call this f as limit t approaches infinity, n of t by 2t. And naturally, though we talk of continuous random logic model, we would normally have our clock signal, and it would be aligning with the clock signal switchings that we will have our signals considered.